Okay, so in the second video on linear programming, I wanted to talk about the notion of variable constraints. So here's an example of a linear program where we've formulated it with this new matrix in vector notation, which is more compact when we write everything out. So there's all sorts of constraints that can appear. Here's a few constraints up top here. There's some mixture of the variables, and so 2x1 plus 1x2 plus 1x3 plus 0x4 is less than or equal to minus 1 is a constraint, for instance. So that's fine, but that's in contrast to a constraint like this. This says 1x1, 0x2 plus 0x3 plus 0x4 is greater than or equal to 3. Or in other words, this is just saying x1 is greater than or equal to 3. And so that's just a constraint on just the variable x1. And so I would call that a variable constraint, and I would kind of treat these, so these are all variable constraints. These bottom four are all variable constraints, and I would treat them as separate from the rest of the constraints, kind of special in a way. And so I'm going to draw a bar here, kind of splitting it off from the rest of the matrix. And I'm going to actually lightly scratch this out, and we're going to rewrite these constraints down below. So it's still important to note that they still are linear constraints in the same sense that these top two are also linear constraints, but they're just special linear constraints in that they're constraints on an individual variable, and it's not obvious right at this moment, but in hindsight it becomes clear that you would want to separate your variable constraints from all the rest of your constraints. So let's do that. So what are these constraints saying? Well, this first constraint is saying that x1 is greater than or equal to 3. The next constraint says that x1 is less than or equal to 5. So I'm going to just put a 5 there, like that. So x1 is greater than or equal to 3 and less than or equal to 5. And then the rest of these say x2 is less than or equal to 1, and x4 equals 2. And so now the way I've written this, we've written some constraints up top, and then the variable constraints at the bottom. And now with this notion of separating your variable constraints from the rest, it's a good idea to make explicit the fact that x3 does not have a constraint on it. It doesn't. The only constraints are imposed on x1, x2, and x4. x3 has been skipped over. So to make it explicit that we're not constraining x3, we can say x3 free. So it's a free variable. x3 is a free variable, and that means it can range over the real numbers however it chooses. Okay. Now if we looked at this just looks like a different way of writing the same thing, but actually there's a way to rewrite any linear program so that for every variable you have, you can write it so that xj is greater than or equal to 0 for all j, from the indices j runs from 1 to n for the number of variables. And this isn't really clear that this would have to be true at all. Certainly in the way we formulated the linear program here, it's not true that each xj has the constraint greater than or equal to 0. But we can rewrite this linear program, and in fact any linear program, so that we can always achieve this. So that every variable has the greater than or equal to 0 constraint, and that's it. So let's see how we can do that. So there's a few cases. In case 1, you can, what if you have xj is greater than or equal to some constant beta? What would you do? Well, you would define a new variable, call it a yj. So we'll replace x's with y's. We'll say yj is xj minus beta. And now, that's a convenient definition to make of a variable, because xj is greater than or equal to beta if and only if yj is greater than or equal to 0. And so I would replace everywhere I saw xj originally in my linear program, I would replace it with yj. I would solve for xj here, so yj would be xj plus beta, and then I would plug that back in everywhere in the linear program above. And then when I write my variable constraints down below, the variable constraint will become yj greater than or equal to 0. And so that would be how you would fix that situation if you have xj greater than or equal to beta originally. So for instance, we have that situation for x1. x1 is greater than or equal to 3. It's also true that it's less than or equal to 5, so there's even more we have to do for this specific linear program, but still, this is the right start. There's another case. What if xj is less than or equal to beta? Well, in that case, we could define an intermediate variable. Xj prime would be. Oh, I'm just realizing now you can't see that. Let me move this up a bit. So xj prime is a new variable that we're defining, and this equals minus xj. And so now we have that xj is less than or equal to beta is equivalent to xj prime being greater than or equal to minus beta. And so why would we have bothered doing that? Well, because now we're in the same situation as we were before. We have a variable, now the variable is xj prime, and it's greater than or equal to a constant. And so what did we do when we had that situation? We defined our variable yj to be that variable, which is xj prime now, minus the constant. And so it's minus beta, which is xj prime plus beta. And of course, xj prime was a middleman variable. We can replace that with the original variable minus xj. So this is minus xj plus beta. And so that's what you would do if you run into this situation. If you have a variable of the form a variable with a constraint of the form xj less than or equal to beta, you replace it with a new variable yj, where yj equals minus xj plus beta. Maybe I shouldn't have closed this box off. Let me put, so this condition we have here, this middleman condition, this is equivalent with yj being greater than or equal to 0, which is what we want. Yeah, there's two more possibilities. What if you have xj equals beta? So for example, up above here we have x4 equals 2. There's a couple ways to view this. On the one hand, you can view this as that means it's both simultaneously less than or equal to beta and greater than or equal to beta, and then you would be in both of these cases simultaneously, and you'd have to do some work. But I think it's just easier to we're just trying to show in general the way we can rewrite programs, so let's not overcomplicate things. If xj equals beta, then xj is not a variable at all. It's a constant. It's the number beta. And so it's just better to no longer view xj as a variable in your linear program. Everywhere you see the variable xj, just replace it with a constant beta, and now you'll have a bunch of constants in places where you used to have a variable, and you just move those constants to the appropriate side of the linear program, so that the left-hand sides of your linear program constraints consist exclusively of your variables, which this variable is no longer one of, and the constants go to the other side. So that's how you can fix this. So let's just say not a variable. It's a constant. So this is actually technically incorrect. It is in fact a variable with this constraint, but it's better to, in principle, not view it as a variable and just replace it with the constant value, and you can immediately get an equivalent linear program by just replacing this with constant. So that's how you can easily fix that. There's one other situation, which is if we have the free variable. So for instance, up here we have x3 is free. So if we have, in general, the variable xj free, so how are we going to rewrite this in a way that there is no constraint on it? So how are we going to place constraints on it to get these greater than or equal to 0 constraints? And it's actually just a bit of a small trick. It's easy to see once it's told to you, so let me just tell it to you. Any number can be written as the difference of two numbers that are non-negative. So let me just say one more time. Every number can be written as a difference of non-negative numbers. So for instance, if I have the number 12, I can write 12 as 15 minus 3, or I could write it as 12 minus 0 is an easy way to do it, in lots of ways. And it's obvious how that works in general for non-negative numbers. For negative numbers, well, I mean, if you have negative 10, for instance, you can write that as 10 minus 20, or you could write it as 5 minus 15, or whatever you want. But the point is that there's always two non-negative numbers that you can write your random number as a difference of. So what that means here is that we can rewrite xj as two new variables, yj plus minus yj minus. So both of these variables, yj plus, these are new variables, and they're both going to be greater than or equal to 0. And since any number can be written as the difference of two non-negative numbers, then this is an appropriate replacement for this variable. So yj plus is the variable that comes first, and then yj minus is the variable that we're subtracting from yj plus, which is why we're calling it minus. So that's how you would fix that. So everywhere you saw an xj in your original linear program, you would replace it with yj plus minus yj minus. And then your variable constraints would be yj plus and yj minus are each individually greater than or equal to 0. So that's how all this would work. And so the real point of all this is that we're trying to standardize the format of a linear program. Right now, there's a whole bunch of different ways a linear program can be written. It's better to have a standard format so that we can demonstrate properties of a linear program, because they all come in some standard format. And this is the road to that. First on that path is the fact that we can arrange to always have our variables be written as non-negative constraints. Every variable is always non-negative, is how you want to write all your variables all the time. That's standardization at play. And this is how you can achieve that, these four possible cases. So you could just kind of stop watching at this point and go on to the next topic, but I'll just do this, plug all this these cases into this situation and just see how it works out in practice. So for example, since this one's just slightly more complicated, but just barely, we'll do that one last. But let's actually, I guess there's really no way of getting around it. It doesn't really matter. None of them are particularly complicated. So let's just do all of them. So what are we going to do? First, we have x1 is greater than or equal to 3, and so that falls into case 1, and so we're going to make a variable y1. Where should I write this? Maybe I should write this somewhere else. It comes along the bottom row, so let me write it down here. So we'll make a variable y1 corresponding to x1, where y1 is equals x1 minus 3. And we're also going to need another variable corresponding to x1. So let's call this y1 superscript a, and is that visible? Yeah, okay. And y1 superscript b. So these aren't exponents; these are just superscripts. So y1 superscript b, or maybe even no, let's just keep it like that. So y1 superscript b will be minus x1 plus 3. Plus 5, plus 5. Okay, and so we just took a look at this constraint, x1 greater than or equal to 3. That fell into case 1, and we figured out how to replace that already. And then similarly, we had x1 less than or equal to 5. That fell into case 2 here, and so we figured out how to do that replacement as well. So what comes next? We have x2 is less than or equal to 1, so we can create a variable y2, which equals minus x2 plus 1, just like case 2 would tell us to do. And finally, we can write we can write x3 can be rewritten as y3 plus minus y3 minus. That's how we can rewrite the variable x3. And so we're going to replace the x's in our linear program here with y's. So let's just solve. So we have y1 a plus 3 equals x1. We have y1b minus y1b plus 5 equals x1. We have minus y2 plus 1 equals x2. I'm trying to do this algebra on the fly. No, not too quick apparently, but anyways, that's what it is. And then finally, I'm just rewriting this one. Y3 plus minus y3 minus equals x3. And yeah, so now we've solved for our variables. And now we just want to replace our variables with these new variables in our constraints here. So let's look at this first constraint, for instance. And what is this first constraint saying? It's saying 2x1 plus x2 plus x3 is less than or equal to minus 1. So how are we going to replace this? Well, actually, we're going to need to replace this with two separate constraints. This is going to be split up into two new constraints, and it's because of the variable x1. You notice down here x1 is rewritten as y1a plus 3 and minus y1b plus 5. And so you might be wondering, well, which way do I replace x1? Do I replace it with this y1a or this y1b? And the answer is you replace it with both, but you do it in separate constraints. So in the first constraint, we'll replace it with y1a, and in the second constraint, we'll replace it with y1b. We need both. Okay, so we replace, so 2x1, so x1, first we'll do the a, so 2 times y1a plus 3. And then that's it. I just replaced x1 with this. And then plus x2. So what is x2 now? It's minus y2 plus 1, and then plus x3, and x3 is now y3 plus minus y3 minus, and then similarly we just and this is all less than or equal to minus 1. I wish I would have left a bit more room, but that's all visible, which is fine then. And then similarly, we just replace the second way to replace x1 is with y1b. So 2 times minus y1b plus 5 plus the same thing, minus y2 plus 1 plus y3 plus minus y3 minus is less than or equal to minus 1. And so we have these two constraints. And then finally, corresponding to this constraint, you would have to do a similar thing. I'm not actually going to bother to write this one out because I hope you get the point at this point. But let's just simplify one of these constraints. Let's take this second constraint here. What we get is 2 minus 2 y1b plus 10 minus y2 plus 1 plus y3 plus minus y3 minus is less than or equal to minus 1. And I have this constant 10 here, and all I do is I just move it to the other side. So let me just, instead of rewriting everything, let me just erase. And minus 1 minus 10 becomes minus 11. That's it. and now I have this constraint written in terms of the variables y1a, y1b, which actually appears y1b, y2, y3 plus, and y3 minus, and all of these variables are greater than or equal to 0. And I do this for every constraint that I saw in my original linear program, besides these variable constraints, of course, all the regular constraints. And finally, you have to replace your objective function as well, and so there's a small question about how do you replace that, because you can't have two objective functions corresponding for each of a y1a and y1b for this x1 variable here, but you can just, in that case, just pick and choose which one of the two you want. You just need one objective function. It's really the constraints that you have to worry about. The objective function isn't going to change no matter how you replace variables, as long as you've replaced all the constraints appropriately below. So for instance, let's just replace it with y1a, just because. And so this will become 2 times y1a plus 3 minus 3 times x2 has now become minus y2 plus 1 plus x3 is now y3 plus minus y3 minus, and x4 is now 2 plus a constant 2. And so what we get is 2y1a plus 6 minus 3y2 minus 3 plus y3 plus minus y3 minus plus 2. I combine all my constants. 6 minus 3 plus 2 is 5. One more time, 2y1a minus 3y2 plus y3 plus minus y3 minus plus 5 is our objective function now. And this is what we're trying to maximize. Okay, now you might just wonder about this constant here at the end of our objective function. We said we wanted linear objective functions. This is not a linear objective function because of this constant, but it is an affine function. Affine functions, if you don't know, it's just a linear function plus possibly a constant, and that's totally fine in our objective functions. You can actually just, maximizing this function is the same thing as maximizing the same function without the constant, because you're just trying to figure out how to change the variables appropriately, and if you just shift up or down by a constant, then it's just the actual output value that changes by plus 5 or less 5. But it's all equivalent in the sense that you can just identify solutions by just adding 5 to, if I just scratch out this 5, just solve this linear program and then add 5 to it, and it's the same thing. On the other hand, you can just say it's totally okay to have constants in your objective function, or in other words, your objective functions can be affine, and that is, in fact, fine. Okay, but that's enough about it. The entire point for all of this was that we can rewrite our linear programs by replacing variables, and now we'll get equivalent constraints, and so everything can be associated back to the original linear program. Solutions to the original can map to the new program, and solutions to the new program can map to the original bijectively, but and the objective functions are going to give the same outputs, but now the advantage is that our variables are always non-negative. So now we have y1a, y1b, y2, y3 plus, and y3 minus are all greater than or equal to 0. And this was not something that we had originally. But these are the constraints that we have now. And so in general, we can always write our linear program so that all our variables are non-negative. And so in general, we're going to max or min, the format can now be viewed as max or min C transpose X, This is, again, the constants. This is the variable vector, such that we'll say A, X, big box, B, just like we did in the previous video, where the box is just kind of a notation for each individual constraint that runs down here. But now we can also say x greater than or equal to 0, where by x we mean the vector x. So the vector x is greater than or equal to the vector 0, which means each individual component is non-negative. And so actually this matrix A, originally we were saying the matrix A was this overall matrix, but now we're scratching out variable constraints and writing them separately. These are the variable constraints down here. The matrix from now on is going to be just the linear combinations of variables, all the mixed constraints that we have here. Maybe I shouldn't use mixed, that's a bit of a loaded word in programming, but anyways, you know what I mean. All the linear combinations of variables, those are the constraints that get written in this, what we're now calling the matrix A. And we're separating the variable constraints down here. And we've just shown that all variable constraints can always be written as non-negativity constraints, like we have here. So this is our new format for linear programs. And so we're working towards standardizing the format of linear programs. And this is a big step forward, basically one half of it. The other half will be in the next video. So thanks for watching.